So now we will start with the discussion where we will use the expression which we have derived for two waves travelling with the same amplitude from both sides. This concept we will use to look at boundary conditions. Now we had discussed earlier that when there is suppose even a semi-infinite string, the amplitude was exactly the same, right, with a phase of 180 degree. You can think like that. The amplitudes are exactly same. So that is the condition which we imposed to see that a wave becomes standing, right? On an infinite string, to get this, what was the condition that we imposed? Just the condition that the amplitude must be same, nothing else. And what happens when you put a rigid end like this? The same thing happens, that the reflected wave has the same amplitude, nothing else, right? Even you don't have to even think about the phase, it is just having the same amplitude, right? That means now here there will be a standing wave. There cannot be a travelling wave in this. Always it will be a standing wave. Yes, because both the waves travelling towards left and travelling towards right, both of them are having the same amplitude. So there is no possibility of any travelling wave in this case. Okay, and it's another way to see that why there cannot be. This is one way to argue. The other way is, see, if some energy comes, there is no way it can go out, it has to go back. So there cannot be any flow, net flow in one side. So that is why it has to be always a standing wave. Okay. Now, so that is the qualitative discussion of that. But now see, so from this expression which we had derived, we can now talk about that same thing. See, this is the space version, and in fact what happens is you have to have a zero displacement condition when x is equal to 0, right? Means here if you have a standing wave, you will have to have something like this only, right? Like that. It cannot be bad. So something like that. It will move because this point has to be fixed now. So one of the node must be that point. So that means this thing has to adjust itself in such a way that this becomes 90 degree and this becomes a sine. Okay. Now, so see, one wave it came, but the other one adjusted in such a way depending on phi plus, because phi plus was your discretion. The person who is standing at infinity, he or she will decide at what phase he or she will start the wave, but the rigid end knows how to reflect it back so that this becomes 90 degree and this becomes a sine, and you get the node at this location, at this location, and then your waveform becomes y of xt becomes 2a, anyway was there. What is the expression? Let me see from here. I always okay, 2a times it will become sine. I will require more space. Array, what's happening? I'll bring it here. 2a sine of kx times cosine of omega t minus phi, some angle phi now. Okay. So this becomes now, you know, the shape of the string, and as usual, again this is a standing wave. The space dependence is completely different than the time dependence. They are split, so it's a standing wave. But have we reduced the number of possibilities which were available here? Not here, yeah, in this case. See, in this, any omega was possible, right? Any omega was possible. You could have excited the string with any frequency of your wish. There was no limitation on the omega which you are exciting it with. But then there was no limitation also on the ratio of a plus to a minus when an infinite string was there. In the case of infinite string, there was no restriction. We impose the restriction just to see what happens in a particular case, but there, the wave doesn't impose any restriction on the ratio of a plus to a minus. But as soon as you put this boundary condition, a single one, that restriction has come into picture. Now the ratio cannot be any arbitrary value, it has to be 1, right? The amplitude. So that means at least we have reduced some number of possibilities, right? Means now still it is infinite numbers. So it was a bigger infinite, now it's a smaller infinite. Okay. So maybe it was having the density of complex numbers, maybe, and not complex number, the real numbers, now it is like a rational number. The densities are different, but both are infinite. But still the omega has got all the freedom, it can be anything. And now when this is happening, we will impose the other side boundary condition. Okay. Then what happens? Then you will have to have, suppose I put this boundary condition here. Then your the other node also now defined. Earlier only one node's location was defined, that it must start at x equal to 0. But now you are saying that even the second node is defined, where it will be, because the length that you have chosen to fix the other end, that's fixed. You have fixed that. So that will tell that, you remember I was talking about here that in a given wavelength there has to be 2 lobes, right? Now here you have to have that, but now you have fixed that L. So that means now L will have that 2 lobes, or in fact, okay, I'll draw that thing maybe. It doesn't require both the thing. There can be a case where I'll draw it. See, suppose this is the case, first case. Then you can have a condition like this, because you had only the restriction that if single wavelength should contain 2 lobes, means to start with. It can be more, but to start with it cannot have half a, means 1/3 of a lobe or something. Now here it is like this. If you consider this imaginary length here, I will not draw that. So there is another lobe over here. So in a way, this is the full wavelength, which has got 2 lobes. That means L is like lambda over 2. Okay. Now in this case, now let's see. Can we go below this? We can't. We can't. So that is the best we can do. Okay. Now here your L will be lambda. In another case, what we can have is I'll make it say case 1. This is case 2, and I'll draw here case 3. And here what I'll do, I'll say that it has got like this. That means this is the wavelength which has 2 lobes, because that is our only requirement. So that means this one is your lambda, which is equal to or I'll say that L has now what? Lambda by 3, so 2 lambda by 3. Sorry, 3 lambda by 2. It has got 3 lambda over 2, because this part is lambda over 2, so 3. Okay, so let's say this is 1, this is 1, and this is 1, right? So what? Now from say now I'll write say case 1. What's the lambda value? It's where did I write? Okay. It's 2L, right? And we have C is equal to F lambda, implies F, the frequency which is existing. I'm trying to get from this geometrical intuition to the frequency which is existing on that, is nothing but C over 2L, right? C over lambda, which is 2L. Now suppose I go to case 2. Lambda will be what? L is lambda, or lambda is L in that way. So your F will be C over L. C over L, sorry. Right? So this is the case 1, where the frequency which is existing there is C over 2L. This is C over L. I'll just write for simple beauty that C over 2L, 2C over 2L. Now if I write say case 3, your lambda is 2L over 3, right? So implies your frequency is C over lambda, so 3C over 2L. Right? Now that means your general frequency is NC over 2L. So the frequencies which can now exist on such strings has been now quantized in a way. You can't have any arbitrary frequency. Earlier it was a bigger or a particular infinite. Now you have still an infinite. N can go from 1 to infinity, but still it's a much smaller infinity, like integer infinity. Countably, uncountable, countably infinite. Okay, that means there is a correspondence between numbers and which you can go up to infinity. Okay, now, and then do you recognize this part? What is this? C over 2L is the time that a pulse takes from one side to go to the other and come back. And that is what we started our discussion saying, that will have something to do with the periodicity of the waves. Now we are saying that yes, so that is the least which can happen. So that will be our fundamental frequency. Okay, but then if the wave can go twice that speed, or not the speed, speed is same, it can oscillate in twice that frequency, so that at a twice or half the time, if it can come back, then still the same everything happens. So this is what is that thing. So this is that fundamental time, and this is 2 times that, 3 times that you are taking. So the frequency is I think 2L over C, sorry, it is N over T basically, not 2L, L, yeah, 2L is the total distance, by C was the time. So got it. So that means you are getting all the frequencies are just getting integral division of that fundamental time period. So those are the possible frequencies, because again it has to be ready, to get the same shape. That's the reason. Whatever has happened in this, now while it is coming back again at the same shape, size, it should be ready, and that is what is told here. Okay. So there are some terminologies which are used here. This when n is equal to 1, so that is, say, f naught, so it's C over 2L, so that's called the fundamental frequency. Okay, of any system. So this is a general term which is not now fixed to a string of finite length, it's a very generic term. Okay, fundamental frequency, that is the frequency, the lowest frequency which can be sustained on a system. And then any frequency over that is called an overtone. Okay, overtone. Overtones are frequencies greater than f naught. Now in some systems any frequency higher than fundamental can exist, but then when these overtones are integral multiples of f naught, they are called harmonics. When if overtones are some integral multiple of f naught. Okay, so one way to express this thing are, so suppose f1 is 2c over 2l, then f2 is 3c over 2l, like that. So one nomenclature is fundamental frequency, first overtone, second overtone, third overtone, like that. And another one is first harmonic, second harmonic, third harmonic, like that. So when any of these terminology is used, so you should understand what they are meaning. In fact, this is the basis of all the musical instruments. That is the word harmonic. Means I think some 500 or 600 BC, Pythagoras had first noticed this, that those sounds, so he did this experiment. He hung a particular weight here, okay, with a given length, and then he struck it. So then some sound came. So he felt it, the feeling he got. Then he changed the length, keeping everything else constant. Then he observed that when this length was 2L, again the sound was pleasing. Okay. The intermediate sounds were not very pleasing when they were played together. So that's more important. Means if you play this sound, it will make some sound. And now if you are hanging 2L, okay, this is 2L. Now you are creating some sound. Now if you play both these sounds here now together, then they will be pleasing if this is there. If you put say 1.3L, those sounds together, they don't feel soothing. So that is what he had observed, that the integral length changes when they are produced and they sound together very nicely. And that is why all the instruments, they have this, suppose you say a guitar, it has got two strings, two ends tied. That means only harmonics will be generated. No normal overtone. They are proper integral overtones which are harmonic. So they will sound soothing when they are played together. Okay. And yeah, we will come to this now. When they are played together is a very important thing. We are going to discuss that now. So that doesn't mean that only mean that you are having different strings and playing that. In fact, on a single string, at the same time, multiple harmonics are being played, and that we are talking about. Are they really soothing or not? So in this case, on a single string, always they will be soothing. On multiple string, that's a different story, but on the single string also, they will create good sounds. Means it's different than a bell which you hit and a string that you pluck. A bell doesn't have this harmonic relationship because it is not tied to both ends. No, it can have any overtone, not necessarily multiple of fundamental frequency. So that is why the sound is not that soothing, because overtones are not integral multiple. But a string tied has this property. That is why when it is hit, you feel better. So that is why it is called a musical tone, that is a shrilling sound. Okay. Okay, so that was about what? The waves on a finite length string. And what is the conclusion? The conclusion is we have restricted the number of possible frequencies greatly. Now they are just like integers, actually natural numbers, not real numbers, not rational numbers, but natural numbers. And then we defined fundamental frequency, overtones, and harmonics. Yeah. So we will stop here for this segment, and we will see in the next segment how to even more quantify these harmonics with respect to the initial conditions that we impose. Okay.